أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. والضحى والليل إذا سجى ما ودعك ربك وما قلى وللآخرة خير لكم من الأولى ولسوف يؤتيك ربك فترضى ألم يجدك يتيما فآوى ووجدك ضالا فهدى ووجدك عائلا فأغنى وأما السائل فلا تنهر وأما السائل فلا تقهر وأما بنعمة ربك فحدث. I seek shelter in Allah from the rejected shaitan. In the name of Allah, the most gracious, most merciful. By the morning sunlight and the night when it falls still, your Lord, O Prophet, has not abandoned you. Not has he become hateful of you, and the next life is certainly far better for you this one. And surely your Lord will give you so much to you, then you will be pleased. Did he not find you as an orphan, then sheltered you? Did he not find you unguided, then guided you? And did he not find you needy, then satisfied your needs? So do not oppress the orphans, nor repulse the beggars, and proclaim the blessings of your Lord. Sadaqallahul Azim.
Vice Chancellor Professor Dr. Bushra Mirza, Distinguished Professor Dr. Sohail Zubairy, Professor Dr. Shehzad Naseem, Professor Dr. Saira Riaz, Deans, Directors, Head of Departments, Dignitaries, Faculty, Young Researchers and students. A very good morning to you all. It is a matter of great pleasure that Department of Physics is organizing a seminar on a very fascinating topic, that is mysterious universe. As Chairperson of Physics Department, I welcome our speaker, eminent and distinguished quantum physicist Dr. Sohail Zubairy. Professor Zubairy's research interests include quantum optics and laser physics. He has been interested in quantum optical applications to quantum computing and quantum informatics. He has also been interested in quantum state measurements of the radiation field and sub-wavelength atom localization. His other interests include coherent atomic effects and quantum thermodynamics. He is the co-author of 2 books, one of quantum optics and the other on quantum computing devices. Recently, he published a book on quantum mechanics for beginners, a good news for all quantum mechanics students. Professor Zubairy received his PhD from University of Rochester in 1978. He held research and teaching appointments at the Optical Science Center of University of Arizona and Center for Advanced Studies at the University of New Mexico before joining the Quaid-e-Azam University. He joined Quaid-e-Azam University in 1984. He served as professor of electronics there and also established electronics department in Quaid-e-Azam University. In 2000, he joined Texas A&M University, where he is presently a university distinguished professor in the Department of Physics and Astronomy and a holder of the Munnerlyn Heap Chair in Quantum Optics. He has received many honors, including the Willis Elam Award for Laser Science and Quantum Optics, Alexander von Humboldt Research Prize, the Outstanding Physicist Award from the Organization of Islamic Countries, the Abdul Salam Prize in Physics, the International Khwarizmi Award from the President of Iran, Hilal-e-Imtiyaz and Sitara-e-Imtiyaz from President of Pakistan, and George H.W. Bush Award for Excellence in International Research. He is an elected member of Pakistan Academy of Sciences and a fellow of American Physical Society and the Optical Society of America. He has published a lot of papers and he has 10,000 citations. It is an honor for me as a chairperson Department of Physics to host such amazing and distinguished international scientists. So I invite Professor Dr. Sohail Zubairy to come on stage and share his knowledge with faculty and students. Big hand for him.
माइक्रोफोन की जरूरत
सर यहाँ पे करना
चल
ये वायरलेस प्रेजेंटर है टेबलेट है
ठीक
आप
समझ गया
ये एरो की भी आप यूज़ कर सकते हैं
यहाँ से
सर नाम के मुबारक
Okay, well, first of all, I would like to thank Dr. Bushra for inviting me to give this lecture here. It's certainly a delightful experience. I mean, Government College Lahore and this Lahore College for Women are really the gold standard of higher education in this country. And certainly it's a great honor to be invited to give a lecture here. What I would like to talk about here would be something that I've been very interested in recently. It's not a research lecture. It's more like what I keep thinking about these days. As a matter of fact, this title, Mysterious Universe, I've chosen because recently I finished a book which is now with the publishers with this same title, with the subtitle being Quantum Mechanics, Relativity and Cosmology for Everyone. So that is sort of the theme that I'll convey. So my hope will be that I can convey to you
सर काइंडली अगर यहाँ पे आ जाए सर वो आवाज़ कम आ
my hope will be that I could convey to you how strange the laws of science are. I mean, some of you being physicists, of course, may know some about it, but really they are stranger than we can think, really. So let me actually start by talking about some brief history. I mean, of course, since antiquity, since the Greek era and even before, People have been trying to understand the basic laws of nature, but it turns out that the progress has been slow and tedious over the years. And I give you 3 examples of how tedious it was to really move from one idea to the next one. So here is my first example, that Aristotle in 4th century BC came up with this notion that all objects are made up of 4 elements, earth, fire, air, and water. And it took almost 2000 years until Dalton in 19th century came up with this idea that all materials are composed of atoms. So the idea of atom had to wait for almost 2000 years. As a matter of fact, sometimes I feel that Aristotle certainly was one of the greatest intellectuals in human history, but sometimes I feel that because of his very high stature, the scientific revolution was delayed by at least 1000 years because people could not and did not challenge what he had to say. The second example I would give you would be about vision. I mean, right now we have a very common sense view about vision, that light is scattered, the reason why I can see you is because light is scattering from you and coming to my eyes. But that was not true. That was not how people understood vision for almost 1000 years. Plato perhaps was the first one, followed by Aristotle and many others who considered vision to be like this, that when I open my eyes to see you, something goes out of my eyes and touches you, and that is how I can feel who you are and the colors and shapes, etc. And this idea, which right now looks very ridiculous, had a reason. I mean, people at that time thought that, like touching, I mean, I had to move my hand to touch something, and listening. So, I mean, the idea was that somehow the vision should be like that. Something should go out and touch you in order to see you. It took almost 1000 years until Alhazen, a Persian, very famous Persian Muslim scientist, who is sometimes regarded as the father of optics and father of modern science, in the sense that he was the first one who really thought that every theory should be tested in a laboratory. So he came up with this idea that really vision is not like that. It is light that scatters and comes to our eyes. The third example I would give, which probably most of us know about, that Ptolemy in 1st century AD came up with this idea that of the planetary system, where Earth was static and all the objects, including sun and the moon and all the planets and the stars, they revolved around the Earth. Something quite reasonable, because at that time gravitation was not known. And it took almost 1500 years when Copernicus first expounded this idea of a heliocentric model, where sun was now at the center, and the planets, including Earth, was moving around. And Earth was now considered an ordinary object rather than the central object, and Copernicus had to face a lot of opposition to that. So this is sort of an example. And then a modern scientific age, one can say it started with Copernicus' realization that we are not at the center of the universe. So that was, I mean, he had to pay a price for it. As a matter of fact, there is a folklore that he got the copy of his book where he presented these ideas on the last day of his life. So he died without knowing the kind of revolution he unleashed. Then Galileo came, but then the defining figure was Newton, who was in the middle of 17th century. And the year was 1666, when Newton was like about in early 20s, and it turned out that there was a plague in Britain, and the universities was closed down, and everybody was sent home. Newton went to his village, and for 1 year he worked there. I mean, this is a scenario which somehow we are all familiar with right now, last 2-3 years. But then he came back with this law of gravitation, and which basically showed that two objects, massive objects, they attract each other, and the attractive force is proportional to the masses of the two objects. But this law had a very important significance in the history of science, as far as I can see. And that was that this was the first time a law had been formulated which could apply to essentially almost everything. I mean, this law could explain why an apple falls on the ground, but this same law could explain how, for example, Earth is revolving around the sun or planets are revolving around the sun. So it had applications or validity over an extremely wide range of objects. And this is the first time that such a law was formulated, and that now became the standard, that if you want to develop a theory, that should not be confined to explaining 1 or 2 or 3 phenomena. It should be able to explain everything. Okay. Newton also formulated, as most of you know, laws of motion. Then about light, Thomas Young, I mean, he did an experiment, double slit experiment, which I'll have time to discuss quite a bit. That will be in some sense my central theme to show how strange quantum mechanics is. But he showed in around 1805 that light consists of waves. This was in contradiction with what Newton had believed. Newton had believed light to be consisting of particles. Maxwell showed that light consisted of electromagnetic waves. This was towards the end of the 19th century. And all these things could be tested in the laboratory. Hardly any phenomenon was at variance with these laws. So there was this feeling that physics was complete. As a matter of fact, a very famous scientist, British scientist, Lord Kelvin, is supposed to have said in 1900 that there is nothing new to be discovered in physics now. All that remains is more and more precise measurements. So this was the thinking. And he could not be more wrong, as we are going to see. So at the end of the 19th century, people thought that physics was very well understood. Newtonian mechanics and wave nature of light, etc., that was ingrained in our thinking, and that sort of remains ingrained with us even today. Okay? And some conclusions, and please think about it whether you agree or disagree, are like this: that we live in a three-dimensional space, up, down, front, back, and left, right, that has existed forever. I mean, if we are given a chance to express, about the universe, this is sort of our view, that it is a three-dimensional space which has lived forever and will live forever. Another thing that we tend to believe is that space and time are completely independent of each other. Time flows from past to present and future, and no matter where we are, 1 second here is 1 second in space, 1 second near sun, 1 second near any other object, but it is independent of space. And this is, of course, appears very, very natural, and nobody can sort of deny it. Another ingrained idea in us is that all objects in the universe obeys laws that are completely deterministic. For example, if I throw an object, a ball, I can predict very precisely, according to the laws of mechanics, where it will hit the wall. There is no ambiguity about it. There is no probability that it will hit there and not there, and so on and so on. Okay? So this is again something which is almost obvious. Light is a wave. I cannot catch it in my hand. It's a wave. And ball is a particle. I can hold it. There is no doubt about it. Light cannot, of course, behave like a particle, and ball cannot behave like a wave. No limit on how fast we can move. According to Newtonian law, if I apply a force, the object accelerates, speed increases. The more force I apply, the force keeps increasing, and there is no limit. I mean, if I keep applying force forever, I can acquire a speed as large as I want. All the matter in the universe consists of atoms, and our idea of the atom is of a spherical object which is piled on top of each other, and that is how any object, the span, myself, and so on, are defined. Ultimate vacuum. I mean, this is a little bit subtle, but a place, let's say a space where there is 0 degree temperature, nothing moves, and it is completely empty. There is no energy whatsoever. You know, if you are in a vacuum, there is absolutely no energy in there. There is only one universe. And when we look around ourselves, there is one universe. And if somebody tells us that there are many universes, that would be a very strange idea, very, very strange idea. But there is no possibility that there are other universes such that we may exist in those universes, but in a somewhat different state. For example, if we are smiling here, there is another universe that exists where we are a bit sad. So these are some of the things that are ingrained in us. We believe in them. Okay? If they are proven, if any one of them is proven wrong, that would be quite strange to us. But the amazing thing, and this is the sense in which this universe is so mysterious, is that none of these things are correct. Okay, I mean, to show each one, I think that would require a 1-hour lecture for each topic. Okay? But just to give you a feeling that how strange this universe is according to the laws that we understand today, none of these very obvious, self-evident truths, as we would like to call them, they are true. And of course, if we realize that the universe appears quite mysterious, really. One thing which I did not list here, which is perhaps the most mysterious of all, is this question of reality. I mean, what we believe is, what we are made to believe is that objects have objective reality. They exist whether we look at them or not. I just came with a car which is standing outside. There is no doubt in my mind that car still is there. If somebody tells me that as soon as I walked in the room, the car basically lost its reality, would appear very, very strange. Okay? So one ingrained idea in us is that all objects that we see around us are real. They continue to exist even when we don't look at it. Okay? So please keep, and this is the theme which I would like to emphasize in the rest of the lecture, and the end result would be startling. So what happened was that at the end of the 19th century, as I mentioned, people thought physics was complete. But what happened was that 2 major revolutions took place at the dawn of the 20th century, completely independent of each other, with one thing common, that Einstein was part of both those revolutions. The first one was the theory of relativity, which was solely due to Albert Einstein. The first ideas were presented in 1905, and the last ideas about gravitation, etc., they were in 1916, and they really revolutionized our understanding of space and time. We cannot look at space and time after learning about this theory of relativity. What it tells us is that space and time are not flat, like what we see. Time is not like equally spaced. They both are curved. The time, for example, for a clock, if you put it on the floor and you put a clock on this rostrum and monitor it with very, very precise instruments, it would turn out that the clock on the floor would be slower than the clock that I place on the rostrum. Amazing. If I go to more massive objects, the time can even further slow down. If somehow we can manage to go near a black hole, unfortunately I won't have time to talk about that, the time stops. We can live forever, okay, if we can survive there. So this is the strange part, the mysterious part of this universe. Then something which even baffled Einstein when he formulated his theory predicted that the universe was expanding. And even Einstein was unwilling to accept this idea that it was expanding, to the extent that he added an artificial term in his equations to cancel this effect of his expansion. But it turned out that about 10 years later, around 1926-27, it was shown that, as a matter of fact, the universe was expanding. When people solved the equations of Einstein without that term, which Einstein later would describe as the biggest blunder of his life, that universe was expanding, and then it was shown through observations that indeed universe was expanding. Why was it so unacceptable to even Einstein? Because what it implied was that if something is expanding, like a balloon, if it is expanding, then there must be a point in the past where it should be like a point from where it expands. So what it implied was that the universe had a beginning. And this was something which even Einstein was unwilling to accept. But it came out, there were a lot of developments, but now it is established, there have been several evidences that indeed universe had a beginning, and universe started 13.8 billion years ago. So the time has not been, it is not, space and time have not existed forever. Actually, time started, whatever it means, 13.8 billion years ago. Scientists don't like to listen to the question, what was there before 13.8 billion years ago? Because there was no time, there was no space. And this is something which we are still battling with, trying to understand it. The second revolution was quantum mechanics, which I would discuss more in this presentation. This quantum mechanics started in 1900, and it provided the laws that govern the motion of objects and their interaction with each other. And the question that I would like to address is the question of reality. They challenge how we perceive our long-cherished concept of reality. Reality of objects independent of us. Okay. So, one thing is that the outcomes that I've mentioned and some things that I'll discuss in this talk may look very, very strange, very mysterious, crazy almost. But the fact remains that these two theories have been the most successful theories in human history. And why do I say that? Because in 100 years, the precision with which we can measure the distance, the time, the temperature, and so on, has increased tremendously. tremendously. But there is not a single phenomenon at this time which is in violation with the predictions of these two theories. So these are very successful theories. Okay, so in this lecture what I would like to talk about is reality real? Okay, and I'll define more formally what reality is, and I'll try to argue using scientific arguments whether, what is the answer to this question. Let me start by this episode which Abraham Pais was an eminent scientist, but he is a biographer of Albert Einstein. Perhaps the best biography of Albert Einstein that has been written is by Abraham Pais. And and he knew Einstein. He interacted with him at Princeton University, and he mentions that we means he and Albert Einstein, discussed Einstein's notions of objective reality which is independent of the observer. I recall that during one walk, Einstein suddenly stopped, turned to me, and asked whether I really believe that the moon exists only when I look at it. This talk will be trying to answer to this question of Albert Einstein. Okay, now let me give you a very brief history for the benefit of those who are fresh to quantum mechanics. Just a brief introduction. I mean, quantum mechanics, as a matter of fact, was born through the solution of a very mundane problem. The mundane problem that had remained, as a matter of fact, unsolved for almost 50 years was this: that you take a metal and you heat it, raise its temperature. And what we know from our observation, that the higher the temperature, the color changes of the metal. Okay, it becomes yellow and red and then blue and so on. Okay, the higher the temperature, the more bluish it becomes, etc. The question that was posed around 1850 was, for a given temperature, what is this color distribution of the light which is emitted by this metal, this heated metal? And this problem remained unresolved for almost 50 years until Max Planck solved it by using some idea which was ridiculous. I mean, even he himself called it a desperate attempt. And that was by treating energy to be quantized in wave packets, not continuum. Okay? I mean, to give you an example, if there is a swing and we are sort of riding on a swing, there is no condition that some amplitudes are allowed and some are not allowed. If I tell you that some amplitudes are forbidden and you can sort of ride only for some amplitudes, that would sound ridiculous. But this is what Max Planck was assuming, that some amplitudes, some energy values are allowed and some are disallowed. One would imagine that when Einstein proposed this idea, there must have been really a big reaction all over the world. I mean, after all, something new was coming up. But it turned out that for 5 years, nobody noticed it. Until 1905, Einstein solved another outstanding problem, which was photoelectric effect, by postulating the notion of photon. Light was finally like a particle, a massless particle. But this was again something very, very surprising. I mean, this was a very, very bold move by Albert Einstein. As a matter of fact, some of you may know, but some of you may not know, that Einstein won 1921 Nobel Prize not for his theory of relativity, for which he is most famous, but for resolving the photoelectric effect. But the reason why photoelectric effect and Einstein's work showing light behaves like photons or particles is very significant, as we are going to see in a moment, that light sometimes behave like waves. This is what we have been taught all along. And now Einstein is telling us that in some experiments, light is behaving like particles. So what is light? Is it particles or is it wave? The third major step that came in was by Niels Bohr, who solved the problem of the hydrogen atom spectrum by making again an ansatz or a postulate, quantization postulate. Okay. And finally, in 1924, de Broglie flipped Einstein's argument. Einstein basically argued that, okay, light was a wave, but in some experiments it behaves like particles. De Broglie argued that electron is a particle, but it should also behave in some experiments like a wave-particle duality. Okay. So this was, okay, I mean, notice that all these phenomena were being explained by some postulate, not a theory. Not a theory which could explain all of them, all of these things, plus everything else in the universe through one equation and one theory. So this was, but these ideas that I list here could not be explained using Newtonian mechanics. So now, I mean, this was really, I mean, 100 years ago at this time, it was a really big crisis in physics because you had some phenomena which could not be explained by a, which could not be explained by the old theory, Newtonian theory, and there was no new theory. But it turned out that soon things changed when in 1925, a 25-year-old Heisenberg, he invented quantum mechanics in the summer of 1925. In 1926, completely independent of Heisenberg's work, Schrödinger wrote down an equation which carries his name, perhaps the most important and famous equations ever written in physics, that is the Schrödinger equation. Schrödinger equation, if you notice, I mean, I don't expect you to sort of follow it, but just notice that this equation is written for a funny quantity that we call psi. So it is for psi. Okay? And this equation essentially is equivalent to F is equal to ma. No similarity whatsoever, okay, with Newtonian laws. But the amazing thing is that Schrödinger could derive the spectrum of the hydrogen atom through this equation, but he did not know what psi was. It was left to Max Born, who was the teacher of Heisenberg. Heisenberg was assistant in Born's group. He basically came up with this interpretation that psi square represents the probability. So now the probability has entered in the discourse of physics. There is no F is equal to ma, rather there is a psi. So when you calculate psi, so if I throw a ball, Schrödinger equation will tell me how psi is evolving, and if it hits, when it hits the wall, there is a psi which is distributed such that psi square, which is a function of position, gives me the probability where it will hit. So now the determinism was gone. Okay. And then it turned out that very soon people realized that they had not just invented an equation, there was an underlying physics which was mysterious or counterintuitive, to say the least. And some of the effects that laid at the foundations of quantum mechanics, one I mentioned, wave-particle duality, quantization of energy, I just talked about, uncertainty relations. We cannot measure the position. I mean, if I throw a ball, Newton mechanics, I can predict where it will be at a certain time and how fast it will be moving. Quantum mechanics tells us it is impossible. I cannot find both of these quantities completely arbitrarily, and this is something which Heisenberg had found, uncertainty relation. And of course the probabilistic description that I just mentioned. I mean, something which really made Einstein very upset. Determinism was gone, now we had probabilistic description. And then there were these notions of coherent superposition. I mean, what we are used to is the door is either open or closed. It cannot be in a superposition of open and closed simultaneously. Quantum mechanically, if I take an atom, which is a ground state and an excited state, it can exist simultaneously in both states. But of course, when I measure, when I observe it, it's either in the ground state or an excited state. Very mysterious and very consequential to this question of reality that we are going to talk about. Based on some of these things, I mean, Heisenberg, who was the inventor of quantum mechanics, this is a quote from him, that not only is the universe stranger than think, it is stranger than we can think. And this is in some sense the theme of this talk. At the end, I hope I will be able to convince with this statement that it is really stranger than we can think. You know, it is beyond our thinking. Several persons, but two big giants, two of the inventors of quantum mechanics were very unhappy about what they had invented. One was Albert Einstein. He was not happy with this probabilistic interpretation. And here he said, well, quantum mechanics is certainly imposing, but an inner voice tells me that it is not yet the real thing. The theory says a lot, but does not really bring us closer to the secret of the old one. I, at any rate, am convinced that he, meaning God, in his mind, is not playing at dice. Okay? That, when the ball is thrown, then it can be either there or there. That the nature should not allow that. Nature should be able to, and the theory should be able to predict precisely where it will hit the ball. To which Niels Bohr is supposed to have replied that Einstein stopped telling God what to do. Niels Bohr was really the champion of the foundations of quantum mechanics, the way we understand it. His ideas, his and Heisenberg's ideas prevailed. Einstein was proven one after another wrong on these issues. Another person was Schrödinger. Schrödinger wrote, this most important equation ever written. He realized what these probabilistic nature, that you can get it there or there, atom in the ground state or excited state. So he said, if we are going to stick to this damned quantum jumping, then I regret that I ever had anything to do with quantum theory. So, this unease has remained with us to this day, even though quantum mechanics has been a very successful theory. All these devices, 20th century was dominated by quantum mechanics. Everything that we see around ourselves is a quantum object. But at the foundational level, it's very disconcerting. Even the founders were very unhappy, and they died with this dissatisfaction. So, for example, Schrödinger came up, let me see if I have, he came up with these paradoxes. He said, okay, you say atom can be in a superposition of two states, ground state and excited state. What about a cat? We never see cat to be in a excited, in a dead, in an alive state. So he, for example, came up with this idea that, no, this doesn't work. Okay, so that supposing we have a box, completely closed box, and there is some radioactive matter there, which is a quantum mechanical object in the sense that it can decay probabilistically. Okay? We do not know when will it decay. It can decay now, or it can decay after, let's say, 1 millisecond, or depending upon what material we are talking about. So it turns out that there is a live cat in the box. If this radioactive matter does not decay, the cat lives. But if this radioactive matter decays, then a particle is emitted, like alpha particle or whatever, and that hits the Geiger counter. This is a Gedanken experiment, a thought experiment. Geiger counter, and then as soon as Geiger counter detects this particle, it unleashes a hammer which hits on a bottle of poison. Poison is released, the cat is dead. So now we have these two situations. If the radioactive substance does not decay, the cat lives. But if radioactive substance decays, then the Geiger counter detects it, triggers the hammer, poison is released, the cat is dead. So we have this situation that radioactive decay does not take place, the cat is alive. If it does take place, the cat is dead, and therefore it is simultaneously in a dead and alive state. But we don't see that. So this was, in some sense, Schrödinger's criticism of quantum mechanics. That, okay, you talk about atoms, but what about a cat? Since I don't see a cat simultaneously alive and dead, something wrong must be with quantum mechanics. It turned out that there was nothing wrong with quantum mechanics. People are still talking about Schrödinger cat, even though it is not a cat, it's like a macroscopic state, as we call it. I mean, my latest paper, as a matter of fact, is how to generate a Schrödinger cat state in the laboratory. But that is not a cat in that sense, in the real literal sense, but a state of light which is very bright. Okay, so I mean, as you can see, the foundational issues, notions of quantum mechanics are philosophical in nature, and before 1970, nobody thought that they would lead to anything practical. The practical was solving the Schrödinger equation for this problem, that problem, that problem, and come up with new devices, etc., etc. Most of the people, even today, are busy doing that. But there were some individuals, they keep still thinking about these foundational issues. Okay? But it turned out that this was not a mental luxury. Okay? Talking about reality and this and that. These are philosophical issues which you would say, well, it's like a drawing room conversation, not a hardcore research project. But it turned out that this gave birth to these fields of quantum communication, quantum computing, quantum sensing, and quantum technology very recently. I wish I had time to go through some of them, but they are the hottest fields right now, quantum technology, for example. This book that I think was mentioned, which I recently wrote, I mean, that describes some of these major developments in great details in that book. So it's not a usual book on quantum mechanics. It's a very, in a way, a very different kind of book. Okay, now we come to the question of reality that I mentioned before, that is what we would like to address. So an object is considered to be real if it exists independent of whether we look at it or we don't. For example, we all believe that moon exists right now, even though none of us is looking at it. Okay? It's hard to imagine that reality is based on what we see. All of us are real because we can see each other, and when we disperse, there is no reality. That is not what we believe. And we feel like we live in a real world. We don't live in a dream. But is it true? I mean, it may very well be that this is a dream that we are all seeing. It is not real. Okay? So, but the question of reality is to see whether objects exist, moon exists when we don't look at it. It turns out, and this is what I would like to show you somewhat, I hope convincingly, that quantum mechanics seems to deny the existence of an objective reality. Very amazing result. If this is true, I mean, it would be stunning. And this would be an understatement. Okay, so let me start with some issues. So, for example, I mentioned that Einstein was not very happy with the probabilistic nature of quantum mechanics. And he, for example, I gave this example that if a ball is incident on a wall, quantum mechanics does not tell us precisely where it will hit, it gives us only the probability where it will hit. Einstein thought that this is not what the theory should do. That a good theory should be like a Newtonian mechanics, which tells us precisely what will happen. If it tells us it will, this is one possibility, this is another possibility, that theory is really an incomplete theory. Okay? So in his viewpoint, a complete theory should be able to give definite predictions. However, quantum mechanics can only tells us whether an event will happen or not probabilistically. So let me highlight it with an example. So here I consider an example of what I call polarization of light. So as I mentioned, light is considered an electromagnetic wave, electric field oscillating, and perpendicular to it magnetic field propagating, and the direction of the electric field is defined as the polarization, as some of you may know. For a single photon, so this is all that we need to know for the present purpose. So supposing I have a single photon which is oriented, let's say, at 45 degrees. Okay. Now, for example, it comes to a beam splitter or to a selection such that it can either pass through vertical or it can pass through horizontal. Since it is at 45 degrees, we would imagine that there is a 50-50 probability. I mean, it's like us, we come to a door, I am walking like this, I come to a door and I encounter a door in this direction and in this direction. Then my probability will be either I will go through this door or through this door. If there was a door in this direction, then of course I will go through it. Okay? But if it is 45, 45. So in this case, what happens is that supposing I have two identically prepared photons, completely identically prepared photon, and then what happens is, this doesn't work. So in this case, what happens is that the first photon, that goes out as horizontally polarized. The second one goes as vertically polarized photon. Okay. They were completely identical. The beam splitter was completely identical. So what went wrong? Why did that happen? Okay. So what was the difference between the two photons? One ended up being horizontally polarized, its electric field became horizontally polarized, and the other one is vertically polarized. Okay? But now we ask a question, what was the state of photon before it hits the beam splitter? Okay? Now this is a difficult question. I mean, the idea is that if somehow we knew the difference, I mean, were they the same? Were they the identical photons? Perhaps they were different. Okay, but if they were different, then we could understand why one of them ended horizontally polarized and why the other became vertically polarized. Okay? But quantum mechanics tells us that, as a matter of fact, there was no difference between these two photons, absolutely no difference. Yet one of them became horizontally polarized and one was vertically polarized. One way out of this conundrum, which Einstein propagated, was that perhaps when we say there was absolutely no difference in quantum mechanics, that is not true. There are some variables that maybe we don't even know about it. We cannot even measure about it. So in a layman language, I might say that, for example, I claim that there is a ghost standing here, which neither of us can see nor measure by any means, but it is there. And if the ghost raises hands like this, then the photon goes up, and if it's in this direction, then it's horizontal. And Einstein argued, but this is my example, of course, ghost is just to understand this notion. And Einstein basically argued that someday, if we are able to find out these variables or something equivalent to this ghost, then we will be able to predict with certainty which polarization the photon will have after passing the beam splitter. And the probabilistic nature will disappear and we will be back to determinism. Okay? So this was his idea. Well, it turned out that, it took almost 30 years. Einstein was already dead for 10 years, that it was shown that actually there are no hidden variables. Einstein was wrong. Okay? There cannot be any hidden variables, there cannot be any ghost. Okay? It's a long argument which again requires some discussion, which I don't have time here. But actually in this case, the problem is even deeper. The question, a very much deeper question we ask. And that question is, what was the polarization state of the photon before being detected? Was it horizontally polarized or was it vertically polarized? Like when the door, if the door is like superposition of open and closed, when we look at it, it is open. We find it open. We immediately conclude that it was open even when I did not look at it. Okay? Can we say the same thing about photon? Okay? Was it horizontal in the first case and vertical in the second case? And as you can imagine, this addresses this question of reality. Is this horizontal polarization in the first case, is this the real property of the photon? That it existed when we had not made the measurement. And for the second photon, it was vertically polarized when we had not made the measurement on the photon. Was it? The quantum mechanics does not, answers to this question directly. But we will see that we can get an answer to this question soon. Okay, so now let me shift gears. And this now is the main part where we address this question of reality directly. But we start with something very, very basic, something which many of you may know. This is the most mathematical slide of my presentation, and this is Young's double slit experiment. Young's double slit experiment, as I mentioned, is very important from a historical point of view, because this was the experiment which established that light consists of waves very decisively, debunking Newton, who believed in particle nature of light. And the experimental setup is like this, that a light wave is incident on a wall which has two slits, and then light passes through, and then on the screen we can get either fringes or no fringes. If we block one of the slits, let's say slit number 2, then we get a pattern which is shown on the third line, I1. If we block the first one, then we get light which is I2. But when we open both of them, then it is like fringes. Bright spot, dark spot, bright spot, dark spot, and so on. I hope many of you have done this experiment. I did it in my FSC, if I recall correctly, with sodium lamp, and I hated it. Now I think people do it with lasers, which is much easier. And here we can understand it, that there is this phase shift, delta. This is the only mathematical part I talk about. It is coming because of that, there is a phase shift. If the phase shift is integral multiple of the wavelength, then we get a bright spot. If it is half the wavelength, then the waves cancel each other, we get a dark spot. Okay? So this is okay. This is something which we have understood for more than 200 years. No qualms about it. Okay? Even though there are something very strange about it, but I don't have too much time for that. Now let's do this double slit experiment not with waves, but with the small bullets, particles. Now in this case, what happens is that if I have a gun sending these tiny bullets, then what will happen is that if slit number 2 is closed, only one open, then we get this curve P1. More bullets will hit the point where P1 is maximum, and similarly for P2. And if both the slits are open, then unlike waves, where we had an interference pattern, we have now no interference pattern. Okay? So the thing is that in this case, we have no interference pattern if we do it with particles. Okay? And the reason for it is that we know which slit it came from. So as a matter of fact, if I want to summarize it, so if I consider these double slit experiments with bullets, this is what I get, no interference pattern. And the reason for that is that for each bullet hitting the screen, I can find out which path it took. It took one of the two. Either it went through one or it went through two. Okay? It could not have gone through both of them. But on the other hand, the light wave, when it is incident and it gives the interference pattern, in that case, the light has to pass through, or photons have to pass through both the slits at the same time. Each photon, in some sense, passes through both the slits to give this interference phenomenon. So this is the key from our point of view. Okay? Is this understood, or should I repeat it? Okay, so basically with bullets there is no interference pattern, and the reason for that is because I have a which path information. Whether for each bullet I know it went through one or it went through two, and so on and so on. Whereas for the waves, each photon essentially passed through both of them. Okay, and therefore I get an interference pattern: bright, dark, bright, dark, spot. Okay. Now let's ask the question. Okay, so this was for the bullets, this was for the light. Let's ask a question: what if instead of bullets or waves, we have individual electrons? Whether we will get this pattern that we get with the bullets, or whether we get the pattern that we get with the waves. Okay, so let's decide in our mind, what do you expect? Okay, if we do the same experiment with electrons, the electrons being sent. Okay, so now it turns out, and this experiment was done around 1960, even though people did not know much about it, that when we do this double slit experiment with electrons, we would have expected electrons to behave like particles, but it turns out that actually it behaves just like waves. They are bright spot, dark spot, bright spot, dark spot. Okay? And here are some simulation results that if I do this Young's double slit experiment with electrons and send each electron one by one, then after 100 electrons, the top picture, where we see a completely random distribution, after 1000 electrons, I see some kind of a pattern appearing, and after 10,000 electrons, it is remarkable that there are regions, dark regions. Electrons do not hit those points. This is, if you think about it, this is a very, very mysterious result. If this experiment was done, let's say, 100 years ago, people would not know how to explain it. How did the electrons know that there are points in there, these dark points, where not to hit? How do they know? Electron is an electron. It should hit randomly, but it avoids some points completely and concentrate on some other points also. Very strange result. Very, very strange result. But a slight twist, slight change, the interference pattern disappears. And that is that by placing some light source in there, which scatters the electron when it is passing through. Can I continue? Okay. So if it scatters, then we can find out which path the electron went. And what happens is that by just very slight change in the experimental system, the interference pattern disappears. Okay? So the finding that there is an interference pattern in this setup is again a remarkable result, and finding that a slight change it disappears. So either we get interference when we have no witch path information, witch path basically when electrons pass through both of them, and we lose interference when we have witch path information. And this is wave-particle duality. As a matter of fact, in the year 2002, there was a survey of eminent physicists to list the most beautiful experiments in physics ever done. And it turned out that Young's double-slit experiment made not one but two appearances on this list. And the first one was Young's double-slit experiment applied to the interference of single electrons, the one that I just talked about. It is so mind-boggling that it made the top of the list. Now at number 5 was, as you can see at the bottom, it was the original Young's double-slit experiment. We were talking about all the experiments that have ever been done in physics. So this is a very stunning experiment, which if you go back home, you might like to think how you would explain that when you send in electrons, there is an interference pattern in the sense that electrons avoid certain locations completely. How can that be? Okay. Well, it turns out that the only way we can explain these results is through a wave function approach. Remember, when there was interference, we talked about electric field. Now there is no electric field for single photon, so we describe in terms of a wave function such that we get interference and no interference depending upon whether we had witch path information or we lost the witch path information. So this is the first principle. So in some sense, from this Young's double-slit experiment, we can derive the first principles of quantum mechanics. Okay? Feynman, who originally proposed this experiment, basically said something like this, that one might still like to ask, how does it work? That there are no photons at some locations. What is the machinery behind the law? No one has found the machinery behind the law. No one can explain any more than we have just explained. No one will give you any deeper representation of the situation. We have no ideas about a more basic mechanism with which these results can be deduced. Okay. Now I come to the most important slide and the last slide, almost the last or second last slide of this talk, the most important one. So please pay some attention. So here I describe an experiment, a earthbound version and a cosmic level version. Let me talk about cosmic level version first, just to illustrate, even though you cannot, it is again what we call Gedanken experiment, a thought experiment, but it brings out this question of reality in a very, very clear manner. So let's suppose there is a star, trillions of miles from here, maybe millions of light years. That means that light originated from there millions of years ago, when perhaps dinosaurs ruled this earth, not we. Light started from there, okay, at that time. Einstein had told us that if there are these massive objects, then light bends around them, making some kind of a lens. So light basically goes around the galaxy on two sides and propagates, and after traveling for millions of years, reaches Earth now. It has started million years ago, but it reaches us now. Okay? So please pay some attention at this point. At this point, when the light arrives us, we make a choice of doing one of the two experiments. One experiment is that we put, so light is coming from there, from here and from here. So what I do is I put a detector in this direction and a detector in this direction. Supposing this photon which is coming from here hits this detector, gives me a click here, then I can immediately conclude, very naturally, that light traveled for all those million years through this right path. If this one had clicked, then I would conclude that the light all those million years was traveling from one side to me. Reasonable. Now supposing instead of putting two detectors, I put a Young's double slit wall in there. Now in this case, which is on the right side, I get interference pattern out of these photons. But this interference can come about only if these photons had traveled both paths. From one path, no interference. It will give me an interference if the light has, for all those million years, was traveling on both paths and combined together in this Young's double slit experiment to give me the interference pattern. So what do I conclude? I mean, what is happening is that my experimental apparatus, very simple choice, either two detectors or an interference setup, determines whether the light for all those million years was traveling through one path or through both the paths. As if we have to go back in time and shape our past million years ago. As if, because at million years ago, photon was released, but now we are deciding whether it traveled only through one path or it traveled on both paths. We are deciding that, but for all those million years. So that means that we are shaping the past by our choice in the present. Amazing. Too much mind-boggling. Too much unacceptable. Okay? How can, we can go back millions of years and shape the past? The other possibility is, which is what most physicists have come to believe, and that is that actually photons did not exist. They were just an idea. They existed only as a consequence of the measuring device. Okay? I mean, depending upon what measuring device we put in there, was it the detectors or was it the Young's double slit experiment, that decided whether this photon behaved like a wave or whether it behaved like a particle. But it had no existence until the detector, until our experimental apparatus was decided. So therefore, so on this basis, one can sort of conclude that the reality is dependent upon what we do, the measurement device, until we don't make a measurement. If we had not made the measurement, in this case, we had not put any of these, then it could be this or that. But physicists would tend to believe that actually photon was just an idea. It came into existence as a result of this of this measurement. Measurement brings about reality. But if you think about it, this is again something very strange. If measurement brings about reality, what if there was no measurement? What had happened when there was no life on this on this planet? Did universe exist? Stars and planets and so on, because there was nobody to make a measurement. So maybe the universe did not exist when we did not exist. And the day we all die, the day the earth comes to a close, perhaps the universe will disappear with us. I mean, these are very tantalizing questions. Okay, food for thought. I'm not giving you the conclusion. I'm just giving you a food for thought that that these conclusions lead to such a strange thinking. So now when I said a mysterious universe, so you agree with me. This is an article which is a very readable article, but I wrote a book now, with the title "A Mysterious Universe," where I discuss all these issues and much more in great details. But this was an article which I wrote with Yakira Harnov, a very famous scientist, very famous. He's an Israeli scientist and myself. And as a matter of fact, this article, Time and the Quantum, Erasing the Past and Impacting the Future, in 2005, we celebrated Einstein's 1905 papers. And this Science published a volume, and they invited me to contribute to this issue of Science, and we contributed this article, which is a very readable article on the subject, but my book, I hope, will be even more layman language. So now comes my final slide. So let me just mention what the founder of quantum mechanics said. The atoms or elementary particles themselves are not real. They form a world of potentialities, not reality, or possibilities, rather than one of the things of facts. So my conclusion, perhaps, to that Einstein's question is that moon may indeed not exist when we don't look at it. So right now, perhaps, there is no world outside this room. Very hard to believe. But we are led to these conclusions not through any philosophy or metaphysics, but by scientific thought and scientific experiments. So I hope I have confused you enough and given you food of thought about, the nature of universe that we look around ourselves is really not what it appears to be. Underlying the laws that govern this universe are truly mysterious. There is, we cannot even rule out the possibility that there is nothing real around us. We are living a dream, for example, and reality lies somewhere else. Okay. With that, I think I come to my conclusion, and thank you again for giving me this opportunity.
We can take a few questions. If any questions or comments, we are welcome. We welcome you for your comments or questions.
After this talk, I think it's very hard not to have questions in your mind. I can imagine that, but anyway.
Yes.
Can you speak a little louder?
So we can. So there is a mic.
Okay, well, perhaps you can.
Assalamualaikum. My name is Sohail Zubairy. I am a PhD scholar. It's quite hard for me to understand the concept of space-time curvature. Why curvature is necessary? Why would we have a curvy space-time curvature? Like we have some examples in space, like we have a stall like and we have a mass in that curve.
Okay, of course, in Newtonian type mechanics, space and time are completely independent of each other. But it turns out that there are some conclusions, and one of them is that the speed of light is constant in all reference frames, I mean, that in some sense ties space and time together, very mysteriously, but yet it does. But the thing is that, I mean, maybe if next year I come, I would like to give a talk on relativity that will really convince you, through some kind of Gedanken experiment, some kind of scientific arguments, that space and space and time are interconnected. If I have, how much time do I have? Because I can. No, I think this will be a much longer argument than 5 or 10 minutes. So, I mean, the point basically is that, okay, let me actually argue. Okay, it may take a few minutes, but let me argue to satisfy you. Okay, what was the foundation of general theory of relativity? So now I'm trying to tell you what is the foundation of this very famous, very difficult, people perceive and so on, general theory of relativity. And here, where does this time and space comes? Okay, so basically, what Einstein, what he described as the most beautiful thought he ever had, this was in 1908, was that what he thought was that if a person jumps from a tall building, free fall, what he realized was that that person will feel he has no weight. Okay, if there is a weighing machine weighing him, it will show 0 because he is in free fall, the weighing machine is in free fall. It is exactly like he is in ordinary space, far away from Earth. Okay. So in that case, so he will not be able to distinguish, if he is in a closed compartment, he will never be able to distinguish whether he is falling on Earth or whether he is roaming around in space. Okay. So this is understood. Then he argued that if I drop an object, it is attracted towards Earth, force of gravity. It has an acceleration. Okay? It is falling under an acceleration on Earth. Supposing there is an object up there in space which is moving in the upward direction with an acceleration. Okay? So now there is a box near the Earth where a person drops and there is an acceleration. But there is a box there which is accelerating upward. It has the same dynamics. You cannot distinguish by dropping an object whether there is any distinction between the two. Agree? So, I mean, if you are in such a box, you can never conclude whether you are on Earth or whether you are accelerating up in the space high above there. Okay? If you follow this, now comes the argument. So then, supposing in that box up there, somebody holds a torch and turns the light on. Where will the light hit? It will go straight and hit that wall at the same height. Okay? But if the rocket is accelerating, then light is released, but the rocket is accelerating, so the light will sort of bend and it will not be at the same height, it will be slightly below that because light is free, I mean, rocket is accelerating. Agree? Now Einstein argued, what will happen if the person on Earth does the same experiment? If I'm staying here and I turn my torch, then what happens? Okay? Our conclusion will be it will hit the same height as the torch, whereas on that rocket it will bend. Okay? So now the question is why? I mean, so what Einstein thought was that his idea that the two reference frames, this is called equivalence principle, either it is wrong or the light on Earth bends. And he concluded, very boldly, one of the boldest moment in physics, he concluded that as a matter of fact, even on Earth, if you do the experiment, light will bend, just like there. Okay? And this bending, but then the question is, why will it bend? Okay, because Earth, according to Newtonian law, a massive, massless object cannot, will go straight. It is not attracted. So he concluded that the only way it can bend is that the space should be curved around, near Earth. And that means that, we are not going on a straight path, we are moving on something like a sphere, where if we throw something, it will bend. Okay? So this sort of explains to you why, how he concluded that space is curved near Earth. Okay? And now I come to the question of what about time? Okay? So the time also can be explained like this, that in this, now there is a bending, and that means that if a light, supposing a second is considered to be going up and down for a light particle. In the bend, when the light bends, supposing we have a clock here. A clock is like this, that the light goes here and comes back, it's 1 second. Okay, it's a special kind of clock. Okay, but so there is a clock here and there is a clock up in space. On this one, Earth, the space is curved. That means when it goes a straight line, it goes not a straight line, it curves. That means it travels a longer distance. That means it's 1 second is slow. Okay. There it will go straight, which is shorter distance. So the time is also, time is slow near Earth because space is curved as compared to far away. And once you put these things together, and it took Einstein about 7 years, the mathematics was very, very complicated, very, very complicated. So it took him almost 7 or 8 years to write down the correct equations for this formalism, but the foundation is this. Now you know what is general theory of relativity. Okay? And that sort of answers to your question, how space and time are intertwined and curved and so on and so on. Okay.
Thank you so much, sir, for the wonderful explanation. We definitely, the student has come to the conclusion that she can now understand something from the space, time, and curvature, and we can also understand few things from your question that discussion that relativity is something to be really fascinating thing, and we will love to hear from you on relativity sometime whenever we will find time for you. I would like to thank our speaker once again. Let's give him a big round of applause. Thank you, sir. So you can take a seat. We will have you back. Now I would like to invite our worthy Vice Chancellor, Dr. Bushra Mirza, for concluding remarks and to present the commemorative shield to the present.
Bismillahirrahmanirrahim. Respectable Dr. Sohail Zubairy, his wife is also with us. It's an honor. Thank you very much for joining us. Honorable teachers, students, I see some guests also here. Assalamu alaikum. It's an absolute honor, sir, to have you among us. A person of such a distinguished career and caliber is with us. It's definitely a source of inspiration. And I'm sure that you have been able to inspire several students, our young researchers, and in future also they will be able to get some guidance from you. I would strongly recommend that the paper which he has mentioned in Science in 2005, I'm sure our young researchers and students will follow that, as well as the book which is written by him, which is for young people. Sir, I'm a biologist, but to be honest, I thoroughly enjoyed your lecture. And actually that also reminds me, when I was a PhD student in Cambridge and working with some DNA running on gel electrophoresis, and molecules move according to their size. Sometimes I had issues and had results which were not being able to, I couldn't explain, and my supervisor used to say that, I said maybe there is something wrong with the gel electrophoresis, and he said, no, I trust physics more than biology, because it's commonly believed that the laws of physics are more reliable than the biological processes, because there is a lot of probability in that. But your lecture actually shows that laws of physics are not that reliable either. So I think that what I have learned from your lecture is that probably now we have started to understand that we don't understand universe. So I think this was absolute honor and pleasure to listen to your talk, and this was just wonderful, to be honest. And I'm sure we will have your contact, which we will be sharing with our students and with our researchers. And because I personally believe that I'm not really sure whether his talk has been able to answer any of your questions, but it must have generated lots of questions. And you will be asking those questions from him, and so we will be, sharing his. I'm sure his contact email is available on University of Texas A&M website as well. But we will be sharing that also with you, so that when you are able to sort of digest this talk as well as read his article and his book, then you will be in a better position to ask questions from him and learn more from him. And in future, we would definitely like to have you, sir, again, sometimes with us. It would always be an honor to stay in touch and see some future collaboration possibilities with your group, learning from you, and definitely hosting you again, because you frequently visit Pakistan. I have just learned, so that would be wonderful to stay in touch. Thank you very much, everybody, and I'm especially grateful to Mrs. Dr. Sohail Zubairy as well, because she's also with us. And thank you very much for joining. Thank you, everyone.
I would like to invite Dr. Zubairy to receive the souvenir, and Dr. Zora and the guests kindly accompany him. Thank you so much.